Dark matter hides some of the universe's most baffling structures, and scientists are still scratching their heads. Stay tuned, because the final object is something almost nobody guesses, and you'll want to hear why it matters. Cloud 9 is a massive, diffuse concentration of dark matter that was first mapped using gravitational lensing techniques in 2015, and it drifts silently through the intergalactic medium. Researchers estimate it contains roughly the mass of a small galaxy, yet it emits no light of its own, making its presence detectable only through the way it bends background starlight. Its elongated shape suggests it may be part of a larger filament of the cosmic web, a scaffold that guides galaxy formation across billions of light years. While the exact composition remains a mystery, scientists believe it is dominated by cold dark matter particles that interact only via gravity. Hidden within this invisible cloud are subtle clues about how dark matter clusters, potentially reshaping models of structure formation. The fact that such a massive object can remain completely unseen challenges our assumptions and fuels ongoing debates about the true nature of the dark sector.
Imagine a gravitational powerhouse pulling entire galaxy clusters toward a single, unseen region of space, and you have the Great Attractor. Discovered in the 1980s through anomalous galaxy motions, this massive concentration of dark matter lies roughly 150 million light-years away, hidden behind the Milky Way's dusty plain. Estimates suggest it contains the mass of tens of thousands of galaxies, though much of that mass is invisible, composed primarily of dark matter and hot intergalactic gas. Astronomers have traced its influence by observing the peculiar velocities of galaxies that deviate from the expected Hubble flow, a subtle but telling signature of a hidden mass. While some recent surveys hint that the Shapley supercluster may share the pull, the Great Attractor remains a dominant, mysterious hub in our local universe. Its existence forces us to confront how much of the cosmos is concealed behind our own galactic veil, reminding us that even our immediate cosmic neighborhood is still largely uncharted.
Surprisingly, the bullet cluster offers one of the clearest visual separations between ordinary matter and dark matter, making it a cornerstone for astrophysical research. In this high-speed collision between two galaxy clusters, the visible gas clouds slammed together and slowed, while the dark matter components passed through each other almost unimpeded, as revealed by gravitational lensing maps. The resulting bullet of hot X-ray emitting gas trails behind a distinct lensing signal that marks where the bulk of the mass, presumably dark matter, now resides. This offset provides compelling, though still debated, evidence that dark matter interacts primarily through gravity rather than electromagnetic forces. Researchers continue to refine simulations of the event, seeking to constrain the properties of dark matter particles, such as their cross-section for self-interaction. The bullet cluster thus stands as a natural laboratory, illustrating how cosmic collisions can expose the hidden scaffolding that binds galaxies together across vast distances.
Hidden within the faint afterglow of the Big Bang, dark flow describes a puzzling, large-scale motion of galaxy clusters that appears to move in a common direction, seemingly defying the uniform expansion of the universe. First identified through subtle temperature variations in the cosmic microwave background, the effect suggests that clusters are being tugged by a gravitational source beyond the observable horizon. Some scientists propose that this could hint at structures from a previous cosmic epoch or even interactions with other universes, though such ideas remain speculative. Others argue that the signal may be an artifact of data analysis or local anisotropies. Regardless, the concept of dark flow challenges the cosmological principle that the universe is isotropic on large scales. Ongoing observations with more sensitive instruments aim to either confirm the phenomenon or rule it out, and whichever outcome prevails will reshape our understanding of cosmic dynamics and the unseen mass that drives them.
Few people realize that the Eridanus Supervoid, an enormous underdense region spanning roughly a billion light-years, may be linked to one of the most enigmatic spots in the cosmic microwave background, the cold spot. This vast void contains far fewer galaxies than average, suggesting a significant deficit of both ordinary and dark matter. Some cosmologists argue that photons passing through the supervoid lose energy via the integrated Sachs-Wolf effect, potentially explaining the temperature dip observed in the CMB. While this explanation is attractive, the sheer size of the void pushes the limits of standard structure formation models, prompting debates about whether new physics or inflationary anomalies are required. Ongoing surveys map the distribution of galaxies and dark matter within the region, seeking to verify its dimensions and impact. Whether the Eridanus Supervoid is a cosmic coincidence or a window into new cosmological phenomena, it underscores how the universe's darkest, emptiest places can hold profound clues about its fundamental nature.
Enormous strands of dark matter weave the universe into a vast cosmic web, connecting galaxies and clusters like an intricate lattice. These filaments, first hinted at in large-scale simulations, are now observed through weak gravitational lensing and the distribution of intergalactic gas. Each filament can stretch for tens of millions of light-years, acting as highways along which matter streams toward dense nodes where galaxy clusters form. While the visible galaxies trace the filaments, the majority of the mass is invisible dark matter, shaping the gravitational potential that guides gas inflow and star formation. Recent observations using the Lyman alpha forest have revealed faint hydrogen clouds aligning with the web, offering indirect evidence of the underlying dark scaffolding. Understanding the filamentary network is essential for piecing together how the universe evolved from a near-uniform plasma to the richly structured cosmos we see today, and it highlights the silent yet decisive role dark matter plays in cosmic architecture.
Beneath the uniform glow of the cosmic microwave background lies a puzzling region known as the cold spot, a temperature depression spanning about 10 degrees on the sky. First identified by the WMAP mission and later confirmed by Planck, this anomaly deviates from the statistical expectations of the standard cosmological model. Some hypotheses attribute it to a massive supervoid along the line of sight, whose gravitational influence could lower photon energies via the integrated Sachs-Wolf effect. Others suggest more exotic explanations, such as imprints from a previous universe or topological defects left over from inflation. While the supervoid theory enjoys support from galaxy surveys, the exact cause remains unsettled, prompting ongoing debates. The cold spot reminds us that even the most precisely measured cosmic background can harbor mysteries, urging astronomers to probe deeper into the interplay between visible structures and the unseen dark matter that may be shaping them.
Mysteriously, the Milky Way's center erupts with twin lobes of high-energy gamma rays known as the Fermi Bubbles, extending roughly 25,000 light-years above and below the galactic plane. Discovered in 2010 by the Fermi Gamma Ray Space Telescope, these bubbles appear to be filled with hot plasma and possibly dark matter particles annihilating or decaying within. Their sharp edges and uniform brightness suggest a rapid, energetic event, perhaps a burst of activity from the supermassive black hole Sagittarius A*, or a series of massive star formation episodes. Some models propose that dark matter interactions could contribute to the observed gamma ray excess, though this remains speculative. The bubbles also contain microwave haze and X-ray emissions, indicating a multi-wavelength phenomenon. Studying the Fermi bubbles offers a rare glimpse into how energetic processes in the galactic core may influence surrounding dark matter distributions, and they continue to fuel lively discussions about the hidden forces shaping our galaxy.
Legendary among astronomers, the Smith Cloud is a massive stream of hydrogen gas barreling toward the Milky Way at about 300 kilometers per second, and its trajectory suggests it will plunge through our galactic disk within the next 30 million years. What makes the cloud especially intriguing is its apparent dark matter envelope, inferred from its surprising ability to remain coherent despite the Milky Way's tidal forces. Simulations indicate that without a dark matter halo, the cloud would have been shredded long ago. Its metallicity points to an extragalactic origin, perhaps a dwarf galaxy stripped of stars but retaining its dark matter core. As it approaches, the cloud could trigger bursts of star formation in the galactic plane, offering a natural laboratory to observe how dark matter-laden gas clouds interact with larger galactic structures. The Smith Cloud thus serves as a dynamic case study of dark matter's role in shaping the evolution of galaxies.
Finally, the Ophiuchus Cluster stands as one of the hottest and most massive galaxy clusters known, with temperatures exceeding 100 million Kelvin and an estimated mass of several quadrillion solar masses, a large portion of which is dark matter. Situated behind a dense region of the Milky Way, it is heavily obscured in visible light, making X-ray and infrared observations essential for study. The cluster's core exhibits a powerful, swirling shock front that hints at recent mergers, while gravitational lensing maps reveal a complex dark matter distribution that does not perfectly align with the luminous galaxies. Some researchers propose that the cluster's extreme environment may host self-interacting dark matter, a hypothesis that could explain the observed offsets. Ongoing observations with next-generation telescopes aim to untangle the interplay between hot plasma, galaxies, and the invisible dark scaffolding that holds the cluster together, offering fresh clues about the nature of dark matter in the most extreme cosmic settings.
We've wandered through clouds of invisible matter, felt the pull of unseen giants, and peered into the coldest voids, each a reminder that the cosmos still holds secrets far beyond our reach. If you enjoyed this journey, subscribe so you don't miss the next mind-blowing list, arriving each week with fresh discoveries that expand our view of the universe. Which dark matter mystery left you most curious? Drop your thoughts in the comments below, and if this video sparked your imagination, give it a like to help others find it. Thanks for watching, and keep looking up.